The action principle roughly states that nature wants to minimize the integral of kinetic minus potential energy over time. This integral is known as the action, hence the name of the principle. However, even though I can mathematically prove that it works, something about it feels deeply unsatisfying because most explanations don't tell me what action actually is, until I found this paper which visualizes the action principle. This video will animate the ideas from the paper, but additionally, we will visualize Noether's theorem because it is only a few steps away. To describe a particle's movement in one dimension, we can specify its current position q, momentum p, and current time t. With these three pieces of information, a state can be neatly summarized as a point in 3D space. This 3D space of all possible states is called the extended phase space. Extended because phase space refers to the two-dimensional space where we don't specify the current time. If we do specify the time, then in principle, given the current state, we should know the state of the particle after a small time delta t. Dividing this displacement by time delta t, we obtain the velocity in the extended phase space, which we denote as u. The t component of u will always be 1 because t increments by delta t in time delta t. If we know the velocity u at every state, then u becomes a vector field. The state of the particle evolves through the extended phase space by following these vectors. The action principle relies on a pretty weird assumption that the divergence has to be 0. However, it isn't immediately over for a vector field like this, where all trajectories converge and the divergence is negative everywhere. Sometimes we can cleverly change coordinates so that the vector fields are transformed to be divergence-free. Here are the details if you want, but don't get too hung up on it. The point is that you can often change coordinates to make the assumption hold. Let's use the mass spring system to get a feel for how all these play out in an actual physical system. Here, Q denotes the extension of the spring from its equilibrium position, which obeys this equation by Hooke's law. The momentum P is mass m times velocity q dot, which allows us to break down the original second-order equation into a set of two first-order equations. These equations tell us how states evolve in the extended phase space, which look like a bunch of upward spirals. So visually, the associated vector field u is divergence-free. If you want to verify the divergence-free property algebraically, it's still not too difficult. The first component doesn't depend on q, the second component doesn't depend on p, and the third component doesn't depend on t, so the divergence is 0 everywhere. In general, we have the vector field u, which tells us everything we need to know about the evolution of the physical system. If you can remember from vector calculus, a divergence-free vector field can be expressed as the curl of another vector field theta, at least locally. This theta is known as the vector potential for u, and the negative sign is just a convention. With the vector potential, we can define something for any path gamma in the extended phase space. We define S to be the line integral of theta along this path gamma, and the integral is exactly the action. You might have three immediate questions when I say this, and we will answer them one by one in this video. The most urgent one for now is how this line integral has anything to do with kinetic minus potential energy. To answer that, let's go back to our old friend, the mass spring system. We have previously deduced the vector field u from the equation of motion, and now need to find the vector potential theta, whose negative curl is u. Later on in the video, we will explore how to find this theta in general, but for now, just for the sake of seeing t minus v jumps out, here is the vector potential theta. You can verify this by explicitly calculating the curl. One thing to note about this vector potential is that the first term of this component is the kinetic energy. This is because the momentum is m times q dot, and so this p squared over 2m is half m velocity squared, which is the kinetic energy. The other term, half kq squared, is the potential energy stored in the spring. Therefore, the vector potential for the mass spring system is P0 minus T minus V. The action we defined integrates theta along the path gamma. With the vector potential we have just described, let's compute the action S. We can substitute in our theta, and the infinitesimal line element dr is the vector dq, dp, dt, which can be written as q dot p dot 1 dt. This changes all the integration variables to t. By computing this dot product, the integrand is pq dot minus t minus v. However, because p is m times the velocity, this pq dot is m times velocity squared, which is twice the kinetic energy. Therefore, this S we defined is really the action we are familiar with. This answers our first question of how this line integral relates to kinetic minus potential energy. What about the next question? It starts with the observation that theta is not unique. You can add a gradient to theta, and it will still be a valid vector potential for u, because the curl of a gradient is 0. That means for a particular u, there are infinitely many vector potentials. A particular choice of theta is known as a gauge. For those who have studied electromagnetism, this concept might look familiar. One of Maxwell's equations states that the magnetic field is divergence-free, and so it also has a vector potential A. And again, the same thing happens where different A's describe the same magnetic field, and a particular choice of A is called a gauge. Conceptually, U and B are measurable. If you know how things evolve, you can uniquely determine them. However, the vector potentials are not measurable, because even if you know exactly how things move, there are many possibilities as to what theta and A could be. The fact that theta is unmeasurable can be used to our advantage. Given U, we want to find that vector potential theta. Let's say we have found a theta. We can add a gradient and it will still be a valid vector potential. By choosing this function cleverly, we can make sure the second component of its gradient cancels what we originally have for theta. This procedure guarantees we have a vector potential with the second component 0. We can do this trick once more. We know that the third component of U is 1, as the t component increments at the same rate as time itself. So we focus on the third component of the curl equation. The left side is 1, and the right-hand side is negative partial derivative of theta q with respect to p. This means theta q is p plus some function of q and t. If you want your vector potential to have 0 as the second component, its first component has to be p plus a function of q and t. But you probably know where this is going. We can add another gradient cleverly. This time, we choose a function g such that in addition to cancelling the c function, it also doesn't depend on p, so the second component remains 0. The upshot is that there must be a vector potential of the form p0 theta t. Let's rename theta t as minus h and call this h the Hamiltonian. To solve for h, just look at the first and second components of this curl equation. This set of equations is known as Hamilton's equations. In this case, we use them to solve for h. The vector potential I presented for the mass spring system was found this way. It also means the Hamiltonian for this system is T plus V, the total energy. Let's go back to how we define the action, the line integral of a vector potential. If we had chosen another vector potential, we would have defined the action differently. But how different? The difference is the integral of a gradient along gamma, which is, by fundamental theorem of calculus, the difference of the values of f at the endpoints. So if we consider the difference in action along different paths gamma 1 and gamma 2 with the same endpoints, this difference is the same regardless of what vector potential we choose. This leads to an important concept. The action itself is unmeasurable because it can take on infinitely many values by choosing different functions f. On the other hand, the difference in action is measurable. It doesn't depend on our choice of vector potential. This answers our second question. S itself depends on theta, but difference in S does not. This answer naturally leads to the third question on the action principle. The difference of two actions can be thought of as an integral around a loop. If there is a surface M bounded by the two curves, by Stokes' theorem, this is the integral of the curl of theta across M. But the curl of theta is by definition negative u, so the difference in action has a visual interpretation. It's the flux of u across the surface, up to a sign. Let's describe the integral in more detail. First, divide M into many infinitesimal area elements. At every one of these area elements, we compute the dot product of u and the normal vector at any point within this region, possibly at the corner. After multiplying dA, the area of this region, we add up the dot products on all the small regions. Now, let's say one of these paths gamma is an actual trajectory a state could take, which means it follows along the vector field u. Then, we vary gamma infinitesimally so that M is only a single layer of these area elements. The difference in action is still the flux across M, but here's the thing. In each area element, u is tangent to the sides because gamma follows u. The normal vector n, being perpendicular to this small area, should also be perpendicular to u. So the dot product is 0, and the infinitesimal difference in action is 0. This is only half of the action principle. All we said is that if gamma is an actual trajectory a state can take, then no matter how you vary your path, delta S equals 0. The other direction is also part of the action principle. Let's consider a curve gamma that is not always following the vector field u. Then there is at least one spot where the tangent vector t is not parallel to the vector field u. One possible variation of the path is in the direction of their cross product. The normal vector in this case is proportional to t cross u cross t, so the integrand looks a bit complicated. However, a property of the scalar triple product is that we can cyclically permute these three vectors. A clever permutation shows that we have the length squared of a non-zero vector, which must be positive. There could be a negative sign depending on orientation, but a consistent choice will guarantee the integrand is either always positive or always negative. So if gamma does not follow u all the time, there is at least one variation with delta S not zero. This is another half of the action principle. At this point, I was a bit hesitant to call the action principle satisfying. In this explanation, the definition of the action S relies on knowing the vector field U already. But if you know U, you can just follow it to see how a physical system evolves. In some sense, the action principle is a bit tautological, pun intended. If you know why this is a pun, comment down below. In practice, you are given the action, or you guess, based on what symmetries you think the physical system should have. The action principle then tells you how the physical system evolves. The main use of the action principle comes from symmetry, which brings us to Noether's theorem, the real reason the previous explanation is satisfying to me. Noether's theorem states that a continuous symmetry corresponds to a conserved quantity. What do we mean by a continuous symmetry? Suppose there is a transformation that takes a path gamma to another path gamma prime. If the actions along the paths before and after are the same, regardless of what path you started off with, then this transformation is called a symmetry. Continuous means, for our purposes, that we can transform infinitesimally. A regular pentagon has a reflective symmetry, but you can't reflect just a little bit. For the circle, however, a tiny rotation is still a symmetry. So, let's say we have an infinitesimal transformation that brings gamma to gamma prime, and the action hasn't changed, so it is a symmetry. If the original path gamma was a physical trajectory, then the action principle tells us that delta S equals 0. In this case, delta S is the long way round minus the original path gamma. In equation form, the long way round is the action along I plus action along gamma prime minus action along F, minus because F goes in the opposite direction. Then, we subtract off the original action along gamma. But now, by our assumption that this transformation is a symmetry, S along gamma equals S along gamma prime, so we can conclude that the action along I is the same as the action along F. This is known as the Noether charge and is the conserved quantity in Noether's theorem. Now that we have a conserved quantity, can we calculate what that is? The action is the line integral of a vector potential theta, but since we are considering a tiny symmetry, and I is an infinitesimal path, this is just the integrand inside. We can expand the dot product with the standard choice of theta, which is p0 minus h, and dr is how the infinitesimal symmetry changes q, p, and t. So the Noether charge is p delta q minus h delta t. If the symmetry is spatial translation, then delta q equals constant and no change in t is a symmetry. It happens for actions like this where a constant translation in q doesn't change the derivatives, hence action unchanged. Applying the formula p delta q minus h delta t, the Noether charge is a constant times momentum, so momentum is conserved. Similarly, for a time translational symmetry, the transformation is a translation in time and q unchanged. Applying the same formula gives Noether charge as some constant times Hamiltonian, and energy is conserved. Now, everything we have done so far is only applicable to motion in one dimension. If we are describing, say, a two-dimensional motion, then there should be two coordinates to describe the position, and two coordinates to describe momentum in different directions. And the extended phase space would be 5-dimensional. In 5 dimensions, we wouldn't be able to use curl. For the higher dimensional case, I've made a second channel video for that. As always, thanks for the patrons, and like, subscribe, and comment. See you next time.